Welcome everyone. This is fifth lecture in the graph theory series. I already have uploaded 4 lectures and I will put the link of those lectures in the pinned comment of this video. So let's start. In this I am going to discuss about Euler Path and Circuit, Hamilton Path and Circuit, Euler's and DIRAC'S Theorem and its related problem. So to understand the concept better, you need to watch the video till the very end, right? So let's start. First of all, what do I mean by the Euler circuit and Euler path? So let us look at the definition first. An Euler circuit in a graph G is a simple circuit containing every edge of G. So our focus here is on every edge, right? So the circuit must contain every edge of the graph. And what is an Euler path? An Euler path in a graph G is a simple path containing every edge of G. I hope you understand the meaning of simple path. When I say a simple path, it means no edge is repeated more than once, right? And when I say simple circuit, means no edge is repeated more than once, right? So let us look at the examples here. We have 3 graphs, G1, G2 and G3, right? And let us look at them and decide that whether these graphs have Euler circuit or Euler path present in them. So let us first look at the graph G1, right? So if you look at the graph G1, here in G1, let us look for a possibility that whether we have a circuit in which every edge is being covered once, or every edge is being traversed exactly once. So here suppose I start at edge A, sorry, not edge A, the vertex A, and suppose from A I move to E, right? So from A I move to E, then from E suppose I move to C, so I move from E to C, then C to D, so I move from C to D, and I am putting arrows so that you understand that here I started, right? I started at this point. I moved from A to E, E to C, C to D, and then D to E. So I am moving from D to E. So I went back to E. Now from E I can move to B. So from E I move to B, and finally from B I move to A. So I move to A. So did you notice one thing, that I have started at the vertex A and I have gone through all the edges exactly once and have arrived at A again, right? Means here this path that I have just traversed is, or rather the circuit that I have created is an Euler circuit, because we started at A, arrived back at A, and in the process I have traveled across all the edges exactly once. So this circuit is an Euler circuit. Now the next question is that what about this graph G2 and G3? So I would suggest you that take a pause and try to find whether the graph G2 or G3 have Euler circuit or not, right? So you should try it and put the answer in the comment section that whether you have got an Euler circuit in these 2 graphs or not, right? I hope you have understood that what do I mean by the Euler circuit. See, I give you the hint, in G2 and G3 both of these graphs do not have the Euler circuit, and we are going to see in the next slides some theorem which will help us to identify the existence of Euler circuit and Euler path. So for the time being you should just pause the video and try to find out that whether an Euler circuit or Euler path exists in these 2 graphs or not. I already have told you that in these 2 graphs the Euler circuit do not exist, but still you should try your way out. And what about Euler path? So here we have an Euler circuit in this graph we can find an Euler path. So what is an Euler path? So suppose I start at the vertex A, right? Here I am starting at A, and suppose I move to C. I am drawing the edge here, I am not writing. So I move from A to C, then I move from C to D, and then I move from D to E, and then E to B, so in this direction, and then I move from B to D, so I arrived here, and then I move from D to A, so I arrived here. I should not stop at A because I want to cover all the edges, so I have to move back to from A to B. So if you look at this movement where I started from A and arrived at B, in the process I have covered all the edges I have traveled, and I have made sure that none of the edges repeated. Every edge has been covered exactly once. But the requirement is that I started at A, but I could not end at A. I ended at B. So even though I have traveled across all the edges exactly once, the circuit is not completed, but the path is completed. So I can start at A and arrive at B. So in the process I have covered all the edges, but since the circuit is not completed, this is known as a or an Euler path. I hope you have understood the difference between Euler circuit and Euler path. In Euler circuit we have to arrive back at the same vertex. In Euler path that requirement is not needed, but in both the situations we must have to ensure that we are walking through all the edges exactly once. Okay, now let us move to the next, and here you can clearly see that we have a directed graph. So let us quickly go through it and find out that whether we have Euler circuit or Euler path in these graphs or not. So I would start with the graph H2 here, the second graph, and in H2 I can see that there is a possibility of an Euler circuit, and I want to show you that suppose you start at the vertex A, and since it is a directed graph you are allowed to move only in the kind of the given direction. You can't move from G to A, you are allowed to move from A to G only. So I start at A, I move to G, right? So this is like I have traveled across this, and then G to C, so I am moving from G to C, and then C2. I think it will be difficult for you to look at the arrow, so let me remove this and just be focused on the screen, otherwise you may miss. So sorry, so I started at A, went to G, or let me write here, I started at A, went to G, then from G I moved to C, so I moved to G to C like this, and then C I went to B, so I went to B, then B I went to G, so I went to G, and then G I went to E, so like this I arrived here to G to E, and from E I moved to D, so I moved to D here, right? From D I moved to F, so from D I moved to F, and from F I moved to A, right? So did you notice that we have completed an Euler's circuit here in this directed graph? Let me repeat the process again, and just look at the screen. I moved from A to G, G to C, C to B, B to G, G to E, E to D, D to F, and F to A. So the graph H2 has an Euler circuit, right? Now what about the other two graphs? You need to find out this and answer me in the comment section that whether these two graphs have Euler circuit or not. This time I am not going to give you the hint. Now what about Euler path? So here in the graph H3 we have an Euler path, and I want to show you that what is that Euler path. That suppose I start at the vertex A from vertex C. So I started at vertex C, I moved from C to A, then from A I moved to B, right? So I moved to B, and then B I moved back to C, so I moved back to C, and then C I moved to D, so I moved to D, and D I moved to B. So you can see that what I did, I just want to show you that I moved like this direction, C to A, then A to B, and then I moved in this direction, so I reached C, and then C to D, and then D back to B. So even though I have not completed the circuit because I started at C, I ended at B, but I have made sure that I have covered all the edges exactly once. So H3 has an Euler path, right? Now I hope by now you are clear about what is Euler circuit and Euler path. I quickly repeat this, that in Euler circuit you have to cover each edge exactly once and you need to complete a circuit. In Euler path you have to cover each edge exactly once, but there is no restriction on completing the circuit, right? So let us move to the next page and look at this theorem which helps us to decide the existence of Euler path and Euler circuit, and these two are very important result. So we don't have to be worried about whether it exists or not. We can quickly decide that whether the Euler circuit exists or not, or whether the Euler path exists or not. So the first theorem tells us that a connected multigraph, and this is applicable for multigraph as well, a connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. Means this condition tells you that if every vertex of the graph has even degree, then it will have an Euler circuit. And it also tells you, because this is an if and only if condition, so it also tells you that if there is an Euler circuit, then it is guaranteed that every vertex will be of even degree. So let us look at this example here. In this example, we note that the degree of the vertex A is 2, degree of the vertex B is 3, here the degree is 2, and here the degree is 3. So this graph can't have an Euler circuit because here every vertex is not of even degree. So G1, no Euler circuit. We just can write directly without thinking much, because of the statement of the theorem, that the theorem requires that every vertex should be of even degree. So this does not have an Euler circuit. Okay. What about this graph? So this graph, the degree of the vertex A is 2, here 1, 2, 3, 4, so 4, here 1, 2, 3, here 1, 2, 3, 4, here 1, 2, 3, 4, here 1, 2, and here 1, 2, 3. So in this graph you noted that here also not every vertex is of even degree, because we have a vertex of degree 3 here and we have a vertex of degree 3 here. So this graph G2 also has no Euler circuit, right? And what about this graph? So we can clearly see the degree of this is 3, the degree of this is 3, the degree of this is 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and this has degree 1, 2, 3, 4, 5, 6. So here like except one vertex, every vertex is of odd degree. So this graph also does not have an Euler circuit, no Euler circuit. Now those students who might be in doubt and they think that the Euler circuit may exist, they should certainly try the possibility, but the statement of the theorem guarantees that Euler circuit will exist if and only if every vertex is of even degree. But here we note that there are two vertices of odd degree. Here also we note that there are two vertices of odd degree. So there is no Euler circuit present in these three graphs. Okay. So now let us move to the next theorem. Okay. So now we noticed about G1, G2, G3, and we decided, because of this result, the first theorem, that the G1, G2 and G3 none of them have an Euler circuit. Now let us look at the next theorem. Next theorem tells you that a connected multigraph has an Euler path, and I already have highlighted the important point, has an Euler path but not an Euler circuit if and only if it has exactly two vertices of odd degree. Now you look at this example here. In this example, we have two vertices D and B which are of odd degree, means we have exactly two vertices of odd degree. So this graph will have an Euler path. It will have an Euler path. It will not have an Euler circuit, because for Euler circuit every vertex should be of even degree, but it will have an Euler path because it has exactly, and I am again repeating, not more than 2, not less than 2. Exactly two vertices of odd degree should be there, and here we have exactly two vertices, that is B and D, both are of degree 3. So that is why the Euler path will be present. And one more thing I want to tell you here, that those two vertices of odd degree, so when you draw any Euler path, these two vertices must be the end point of that Euler path. So let us try to draw the Euler path in this graph. So suppose I start with the vertex D, or I can start with the vertex B, because I told you that these two vertices will be the end points of the Euler path. So if I start at D, I can move from D to A, suppose something like this, D to A, and then A to B, right, and then B to D, B to suppose I say C, B to C. I repeat it, D to A to B, B to C, C to D, and then again D to B, right. So you saw what I did. I started at D, and after going through all the edges exactly once, I arrived at B. So this was the end first point of the kind of path, and this was the end point. So both the end point, the first point and the last point, are the vertices of degree 3. Okay. Now if you look at this graph here, gentlemen, here also you can see that you have exactly two vertices, that is D and B of odd degree. So this has no Euler circuit but has an Euler path, and to find an Euler path we can either start at D or I can start at B, right, because these 2 points will be the end points. So if I start at B in this case, I can, let me draw the Euler path here. So I can move from B to A, I am starting at B, then from A I can move to G, then from G I can move to F, then from F I can move to E, from E I can move to D, from D I can move to C, from C I can move to G, from G I can move to B, so something I went back, and then B to I can move to C, and from C I can move to F, and from F I can move to D. So we have actually covered all the edges exactly once, and I started at B, which was a vertex of odd degree, and I ended at D, which is also a vertex of odd degree. So the existence of Euler path was guaranteed because of there are two vertices of odd degree present in this, and we also have shown you that when we are starting at B, one of the vertex of odd degree, we are ending at D, another vertex of odd degree, and you can see the movement from B to A to G, G to B, let me repeat, B to A to G, G to F, F to E, E to D, and then C, and then G, and then B, and then C, and then F. So and then back to D. So this is how the Euler path will look like, right? You should pause the video and try to draw the Euler path starting from D and ending at B. Okay. Now this does not have an Euler circuit, and it will also not have an Euler path because the existence of Euler path is required because of, the existence of Euler path is possible only when there are exactly two vertices of odd degree, and here we have multiple vertices of odd degree, so it will neither have an Euler circuit nor it will have an Euler path, right? So let us take some more example. If I look at this example here, the vertex A is of degree 2, D is of degree 4, G is of degree 2, H is of degree 4, I is of degree 2, F is of degree 4, C is of degree 2, E is of degree 4, and this is of degree 4. So every vertex present here in this graph is of even degree. So it is guaranteed that it will have an Euler circuit. And let us quickly draw the Euler circuit here. So suppose I start at A, I go to B, then from B I go to C, from C I go to F, from F I go to I, then I to H, and then H to G, and then G to D, and then D to E. Let me move from D to E, and then E to H. So let me go back from E to H, and what we can do next with E to H, and then H to F I can move, H to F, then I can move from F to E, and then from E I can move to B, and B I can move to D, and from D I can move back to E. This is a long kind of Euler circuit, but I hope you have understood. And if you have not, please pause the video and repeat the video again, so that you see that how I have started at B and ended at B. See, once I was aware that it will have an Euler circuit, then we can use the trial and error and try to find an Euler circuit. Because if someone is telling me that find an Euler circuit, and I know because of the theorem that every vertex is of even degree, so Euler circuit is guaranteed, so that certainly we can find. Yes. Now, ladies and gentlemen, if you look at this graph, the degree of this is 1, 2, 3, 4, so 4. The degree of this is 1, 2, 3, 4, so 4. The degree of this is 1, 2, 3. The degree of this is 1, 2, 3, 4. The degree of this is 1, 2, 3, 4. And degree of this is 1, 2, 3. So here no Euler circuit, because Euler circuit requires that every vertex should be of even degree. So no Euler circuit is present. But because there are two vertices of odd degree, that is C and F, so it is guaranteed that it will have an Euler path. But Euler path is present. So what will be that Euler path? And we also know that F and C will be the end point of the Euler path. So let us quickly find out. Suppose I start at F. So from F I can move to A. From A I can move to B. From B I can move to C. From C I can move to D. From D I can move to E. From E I can move to, suppose I say F. From F I can move to B, and from B I can move to D, and from D I can move to what? From D I can move to A, right? And from A I can move to E. So from A to E I can move from this direction, and finally we move from E to C. So we have completed the Euler path, because you can see every edge has been covered exactly once, and we started at F, we ended at C, because these two must be the end point. For your convenience, I am also writing this, because some of you might be thinking while I was drawing, you must not have been like able to locate it. So let me draw the Euler path for you. So I move from F to A, then I move from A to B, and then B to C, and then I move from C to D, and then I move from D to E, and then E to F, right? I'm moving in this direction. Sorry, let me write it like this. From E I move to F, okay? And from F, where did I move? From F I move to B. From B, where did I move? From B I move to D, and then from D I move to A, and then A I move to E, and finally E to C. So this is an Euler path. We started at F, ended at C. So I hope the concept of Euler path and Euler circuit is clear to you. Now let us move to the next thing. So what is Hamilton path and circuit? So in Euler path and circuit, it was required that every vertex must be, traveled across or traversed exactly once. In Hamilton path, if you look at the definition, it tells you that a simple path in a graph G that passes through every vertex, not every edge. Now it requires that you have to pass through every vertex exactly once is called a Hamilton path, and a Hamilton circuit in a graph G that passes through every vertex once is called a Hamilton circuit. See, in Hamilton circuit, certainly the first and last point will be the same, because circuit requires the initial and terminal point to be the same, but other than that, every vertex must be passed through exactly once. So if you look at this graph here, this graph I have taken 3 examples, and what do you think that whether we have in G1 a Hamilton circuit? So clearly we can see that in G1 we have a Hamilton circuit. We can start at A, go to B, B to C, C to D, and D to E, and then E to A. So clearly it has a Hamilton circuit. Like I start here A, I went to B, I went to C, C to D, D to E, and E to A. And I repeat again, when I am saying Hamilton circuit means I have to touch every vertex exactly once. So I started at A, went to B, so I touched B, then I went to C, so I touched C, then I went to D, I touched D, and then I touched E, and then I went back to A. So there is a Hamilton circuit here. Now this graph G2 does not have a Hamilton circuit, and because if you start at A and if you go to B, right, so how will you come back to A? Because if you come back to A, you if you go in any direction, you must have to touch the vertex B again. So this can't have a Hamilton circuit. No Hamilton circuit. I hope you are getting my point. I repeat my argument that if I start at A and go to B, so I touched A, I touched B, now I have to touch C, right? So if I touch C and suppose I touch D, then to go back to A, I have to touch, B again. So because of this AB, it is not like we have to start at A. If we start at C also, so if you go to C to B and then B to D, and how can you go to A? So certainly there is no Hamilton circuit. I am also going to talk about a standard result which will help us to identify the point that this graph will not have a Hamilton circuit. But certainly there is a Hamilton path here, because if I start at A, so I started at A, then I went to B, and then from B to C, and then C to D. So I start at A, go to B, B to C, and C to D. So every vertex has been touched one. So the circuit is not completed, but the Hamilton path is present. So there is no Hamilton circuit, but let me write here, but Hamilton path exists, right? And what about this graph? So I leave this for you to verify that G3 does not have Hamilton path. So here I am saying no Hamilton path, and also no Hamilton circuit is present in this graph. And reader, or like the student whosoever is watching the video, should try to verify this, that there is no Hamilton path and no Hamilton circuit present in this graph. Okay, so now let us move to the next. So now let us look at this remark. It tells us that there are no known necessary and sufficient criteria for the existence of Hamiltonian circuit. However, many theorems are known to give sufficient condition for the existence of Hamiltonian circuit. Ladies and gentlemen, I hope by now you are clear about what is necessary and sufficient condition. If a sufficient condition means that if this condition is true, then it is guaranteed that a Hamiltonian circuit will be there. but it is not necessary. It is also possible that if this condition is not true, still the Hamiltonian circuit may be present. Okay, so like we have seen earlier, we had a necessary and sufficient condition for the existence of Euler path and Euler circuit, but here in case of Hamiltonian path or circuit, we don't have a necessary and sufficient condition. So what are these two results which helps us to decide that the existence of Hamiltonian circuit is there or not? So look at this. Certain properties can be used to show that a graph has no Hamiltonian circuit, and one of such properties that a graph with a vertex of degree 1 cannot have a Hamiltonian circuit. So since if you look at this example has a vertex E which is of degree 1, so in this graph there will be no Hamiltonian circuit, right? No Hamiltonian circuit, right? So this is a very easy way to look at the result, that okay, if we have a vertex of degree 1, it can't have a Hamiltonian circuit. The second result tells us that if a vertex in a graph has degree 2, then both edges that are incident with this vertex must be a part of any Hamiltonian circuit. So to understand this, let us look at this example. In this graph, we have a vertex of degree 2, we have another vertex of degree 2, this is also a vertex of degree 2, and this is also a vertex of degree 2, and this vertex is of degree 4. So if we draw any Hamiltonian circuit, for example, let us take the vertex A here. So since A is of degree 2, it has two edges incident on this edge, and this edge. So both these edges must be a part of any Hamilton circuit. So let us try to draw the circuit here. Suppose I start at A, and there are two possibilities. Either I can move from A to C, or I can move from A to B. So let us explore both of them. If I move from A to B, and since I want a Hamilton circuit, so I have to touch all the vertices. So if I start at A, move to B, then I have to move to C, right? And from C there are two possibilities. Either I move in this direction, or in this direction. Rather, three possibilities are there. So if I move in this direction, I will not be able to come back to A without repeating the vertex C, right? If I move in this direction, in the direction of A, I won't be able to go to E without repeating the vertex C, right? Same is true for other vertices as well of degree 2, like D, E, B and A. If you start at any of them, you will realize that no Hamilton circuit is present. So whenever we have a situation where any vertex is of degree 2 present in the graph, then that vertex must be a part of any Hamiltonian circuit, and then we can give our argument that whether such Hamiltonian circuit will exist or not. Okay, now let us take two quick example again. So if I look at this example here, this graph will not have a Hamiltonian circuit because we have a vertex of degree 1. So no, it does not have a Hamiltonian circuit. What about this? So here again, if you look at this vertex, it is of degree 2, this is of degree 2, this is of degree 3, this is of degree 3, this is of degree 2, and this is of degree 2. So since A is of degree 2 and there are two edges incident on A, so both of these edges must be a part of any Hamiltonian circuit. This is what the requirement was, that both the edges must be part of any Hamiltonian circuit. Okay. So if I start at A, let us explore this example. So if I start at A, suppose I go to C, right, or I go to B. There are only two possibilities. So if I go to C, and since I want a Hamiltonian circuit, so I have to cover B also. So if I go to B, then to cover F I have to repeat C. But if I go to F, then to cover B, again I have to repeat C. So it is not possible without repeating C to cover all the vertices. So this will also not have a Hamiltonian circuit. Okay, I hope you are getting it. Now we have two very interesting results. One is known as DIRAC'S theorem and another is known as Euler's theorem, and we are going to solve some problems related to that as well. So first look at the statement. Dirac's theorem tells that if G is a simple graph with n vertices with number of vertices greater than or equal to 3, such that every such that degree of every vertex in G is at least n by 2, then G has a Hamilton circuit, and this is a sufficient condition. It is not a necessary condition. Means if this requirement is true or this requirement is fulfilled, then existence of Hamiltonian circuit or Hamilton circuit is guaranteed. But without this requirement being fulfilled, the graph still may have a Hamiltonian circuit, right? We will see through examples. Second is Euler's theorem. So what is Euler's theorem? It tells you that if G is a simple graph with n vertices with a number of vertices greater than or equal to 3, such that degree of U plus degree of V is greater than or equal to n for every pair of non-adjacent vertices. I repeat, non-adjacent vertices U and V in G, then G has a Hamilton circuit. To understand this, let us look at some example. So here in this example, they are saying that for each of these graphs, and there are 4 graphs here, I will be talking about graph A and graph B on this page and C and D on the next page. So what is the question? Whether these graphs, for each of these graphs, determine whether Dirac's theorem can be used to show that the graph has a Hamilton circuit. Second, whether Euler's theorem can be used to show that the graph has a Hamilton circuit. And third, whether the graph has a Hamilton circuit. So as I told you that Dirac's theorem and Euler's theorem are sufficient condition. These are not necessary condition. So even though if they are not being true, still the graph may have a Hamilton circuit. So look at the first example. If you look at this example, the degree of this vertex is 2, and let me write here A. What is the number of vertices in the graph? 5, because this 2, 1 2 3 4 5, there are 5 vertices. And the first part is whether Dirac's theorem can be used. The answer is no. Why we can't use Dirac's theorem? Because Dirac's theorem requires the degree of each vertex to be at least n by 2. So what is n by 2 here? N by 2 here is 2.5. So degree certainly can't be 2.5. So in this case the degree should be at least 3. So the degree of a vertex should be greater than or equal to 3, right? Because n by 2 is 2.5 and the degree of a vertex can't be 2.5. So for n by 2 to be greater than or equal to 2.5, it should be greater than or equal to 3. But here we have a vertex of degree 2, so we can't apply the Dirac's theorem. Second, can we apply the Euler's theorem? So let me quickly rename the name the vertices A, B, C, D and E, and look at the vertex A and look at the vertex C. Look at the vertex A and C, and one thing you notice that A and C are non-adjacent vertices. There is no edge between A and C. And if I take the degree of A plus degree of C, that is 2 plus 2, this degree is also 2, so 2 plus 2 is equal to 4. And the Euler's theorem requires that degree of sum of degree of a pair of non-adjacent vertices should be greater than or equal to n. It means what? That here degree of A and degree of C, that is equal to 4, it should be greater than or equal to n. So what is n here? 5. But certainly 4 is not greater than or equal to 5. So we can't apply the Dirac's theorem here. No. But third part of the question is whether the graph has a Hamilton circuit. So clearly the graph has a Hamilton circuit. I can start at the vertex A, go to vertex B, so we touched B, then go to vertex C, we touched C, then C to D, we touched D, and D to E, so we touched E, and then E to A, so we touched A. So there is a Hamilton circuit, A to B to C to D and to E, and then E to A. So even though the Dirac's theorem, this is the Dirac's theorem. Even though the Dirac's theorem and Euler's theorem are not applicable, still the graph has a Hamilton circuit. So that is why I told you earlier that Dirac's theorem and Euler's theorem are sufficient condition. These are not necessary condition. It means what? That even though if these are not true, still the graph may have a Hamilton circuit. Now if you look at the example B here, I am solving B here. Here B also, the first part, first is n is equal to 5. The number of vertices are 5 here. So what is the first part? Can we apply the Dirac's theorem? The answer is no, because here we have a vertex of degree 2, and every vertex to apply the Dirac's theorem, every vertex should have degree at least n by 2. So n by 2 here is what? N by 2 here is 2.5. 2.5 can't be degree, so here 2 is certainly less than 2.5, so we can't apply the Dirac's theorem, right? What is the second requirement? Second requirement is that the sum of degree of every non-adjacent pair of vertices should be greater than or equal to n. So if I take the example of the vertex degree of the vertex A and degree of the vertex D, degree of D, what do we notice? That this is degree 2, this is also degree 2. So degree of A is 2 plus 2, this is equal to 4, but 4 is certainly not greater than or equal to 5, which is the number of vertices. So we can't apply the so this Dirac's theorem can't be applied here. The Euler's theorem also can't be applied, and I hope you have got the explanation. And C part is that whether there is a Hamilton circuit. So here also there is a Hamilton circuit. Start at A, go to B, B to C, C to D, D to E, and E to A. So every vertex has been touched exactly once, right? Now let us look at these two examples on the next page. So now let us look at the C part. So first of all, in C part, how many vertices are there? N is equal to 5. Let me call these vertices A, B, C, D, and E. First part of the theorem is, can we apply the Dirac's theorem? So Dirac's theorem tells that degree of each of the vertex should be at least n by 2. So what is n by 2 here? N by 2 here is 2.5. And if I look at the degree here, it is 3, 3, 3, 3, and 1, 2, 3, 4. So degree of each of the vertex is, degree of each vertex is greater than, or equal to 2.5. At least 2.5 actually means what? That minimum degree should be 3. So we have the degree 3, 3, 3, 3, and this degree is 4. So we can apply the, Dirac's theorem. So yes, we can apply. And since using Dirac's theorem, we can say that a Hamilton circuit is guaranteed here. It is guaranteed that a Hamilton circuit is present, right? What is the second part of this problem? Second part is that can we apply Euler's theorem? So for Euler's theorem to apply, because if you take any two non-adjacent vertices, because the minimum degree is 3, so for any pair of non-adjacent vertices, degree of U plus degree of V, and U and V may be anything. I hope you understand it, that I am selecting any random two vertex which are non-adjacent. Non-adjacent means, suppose I select the vertex A, then we can't select B, E, and D. We have to select C. So if you select any two non-adjacent vertices, and since minimum degree is 3, so this must be greater than or equal to 6, and 6 is certainly greater than or equal to 5, because the number of edges is number of vertices here in this graph is 5. So 6 is greater than or equal to 5, so we can apply the Euler's theorem as well. So Euler's theorem also guarantees the existence of a Hamilton circuit. And third part of the question is that whether we have a Hamilton circuit. So since it is guaranteed by both the Dirac's theorem as well as the Euler's theorem, so let us find a Hamilton circuit here. So what is the Hamilton circuit here? So let us find a Hamilton circuit. Let us start at the vertex A. So cover the vertex A, move to B, so cover the vertex B, then move to C, cover the vertex C, then move to E, cover the vertex E, then move to D, cover the vertex D, and then move back to A. So you see we have completed a circuit. Let me repeat it: A to B, B to C, C to E, E to D, and D to A. So in this way we have completed a circuit whose initial and terminal vertex is A. So the third part of the question is, yes, there is a Hamilton circuit. Now let us solve the last question, D question here. So in D, how many vertices are there? We have 1, 2, 3, 4, 5 and 6 vertices. And what is the degree of these vertices? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 and 1, 2, 3. And what is the requirement of Dirac's theorem? That degree of each. So first of all, what is n? N here is equal to 6, right? And what is the requirement for the Dirac's theorem? That degree of each of the vertex should be at least n by 2. So what is n by 2? N by 2 is equal to 6 by 2, which is equal to 3. So we can clearly see that each of the vertices of degree 3. So the Dirac's theorem can be applied. Yes. Second is that can we apply the Euler's theorem? So Euler's theorem tells you that degree of two non-adjacent vertices, that is degree of u plus degree of v, should be greater than or equal to n. What is n here? N here is 6. So if you take any two non-adjacent vertices, the degree is 3, so 3 plus 3 is equal to 6, and 6 is certainly greater than or equal to 6. Then certainly we can apply the Euler's theorem as well. And third part of the problem is that whether we have a Hamilton circuit present, so that we have to find out. So let us find out a Hamilton circuit in this graph. So what is the Hamilton circuit here? To move, we start at A. So I start at A, go to F. So A vertex is covered, F vertex is covered. Then from F move to B, so B vertex is covered. Then move to C, so C vertex is covered, right? And then C to E, so E vertex is also covered. Then move from E to D, so D vertex is also covered. So we have already covered all the vertices, and since we have to complete the circuit, I can move from D to A, right? So here the circuit is also available. So these four problems we have understood that when we can apply the Dirac's theorem, when we can apply the Euler's theorem. I also explained that Dirac's theorem and Euler's theorem are sufficient condition. If Dirac's theorem is true, then certainly the graph will have a Hamilton circuit. If Euler's theorem is true, then also certainly the graph will have a Hamilton circuit. But if these two are not true, still the graph may have a Hamilton circuit, because these two are not the necessary condition. So we have discussed a lot of things in this video, and this is a very interesting topic. I hope you all have understood it. In case if you are able to watch the video till the very end, I would suggest you to like the video and share with all your friends so that they are also benefited by this. So that's all from my side in this video. Thanks for watching.